Welcome to Almost Here, Round the Corner Future Technology podcasts with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with the Future Tech Podcast. My guests are Professor Stephen Chase and Professor Byron Yu. They're both at Carnegie Mellon University, and we're going to be talking about their research into biomedical engineering and brain-computer interfaces. So, Professor Chase and Yu, how are you doing?
Good, thanks. How are you?
Good. Yeah, thank you for coming. Let me know if it's, the work that you're both working on. Yes.
Yeah, great. So one of the things that we've been working on is brain-computer interfaces, where the idea is that you connect the brain to a computer cursor or a robotic limb, and you can allow a person to control the computer cursor or the robotic limb just by thinking about it. So, for example, the person can think right, and then the computer cursor will go right. Or if the person thinks left, the computer cursor will go left. And most people in the field, including us, are interested in helping paralyzed people regain movement using a brain-computer interface.
Right.
And we have a sort of a novel approach or a use of a brain-computer interface, which is to use a brain-computer interface to address basic scientific questions about how the brain works. Right? So basically using a brain-computer interface as a tool to study the brain.
Yeah, probably a famous example of this, and I don't know how close it is to what you're doing, but I guess Professor Stephen Hawking that recently passed, what was he doing? How was he communicating to the computer? Was it a brain-computer interface, or was it a different format than what you're working on?
Yeah, that was a little bit different. I believe his device worked. He had a straw that he would blow into, and that gave him control over the wheelchair and I think over his spelling device. The stuff that we work on, what we do is we record activity directly from the brain, and so we'll have electrodes directly implanted in primary motor cortex, which, as the name implies, is the part of the brain that's responsible for movement. And we'll look at the activity of those neurons, and then we'll translate the intended movements that the subject wants to make. And so the idea here is that you can take a patient who's paralyzed for whatever reason. It could be ALS like Stephen Hawking had, or it could be stroke or spinal cord injury, and you can translate their intended movements directly from the activity of the neurons in the brain, and then apply that to any kind of device, a wheelchair, a spelling device, a cursor on a computer screen, and then you can bypass the damaged tissue and allow them to interact with the world that way.
Well, the process sounds very invasive, obviously, for the patient, and I know you wouldn't do this unless it was a super serious circumstance where they were, paralyzed to the point where they're locked in or they're unable to use arms or legs or do much. But any hope of doing this with a scalp cap or a non-invasive way, or we're not there yet?
Yeah, I would say there are a lot of people working on that problem, because obviously that's what you would want to do. There's no surgery involved, and if an electrode breaks, you just replace it. And right now, I would say the information content just isn't there yet. You can get basic control signals out of a EEG skull cap, but you can't get complex control over a high degree of freedom robotic arm, or you can't get grasp interactions, that sort of thing.
So when you're doing the surgery and linking directly into neurons, is the cut covered up, and is the person able to, to be outside of the hospital environment and lab, or do they have to? Is it left open, and does it have to be attended to all the time?
No. So, in the clinical trials where this is done, patients are sewn back up. So the electrodes are implanted, and then everything's sewn back up, and you have a plug that's sort of attached directly to the skull that you can connect and disconnect. And so it works in that sense a lot like a cochlear implant. So the patient can go about. They can leave the house. They can walk or not walk around, but they can leave the house and are still mobile in the wheelchair.
So how many neurons do you have to connect to get some fine degree of control? Hundreds, thousands? What level are you at?
Yeah, so a typical number with the current technology is many tens of neurons, maybe 100 or 200 even. And in recent developments in neural recording technology is probably going to allow us to record from even more neurons in the coming years. So in terms of the level of control that one can have of a computer cursor or robotic limb, right now with around 100 neurons, you can control a computer cursor very well. So recent work has shown that that brain control of a computer cursor is half as good, or maybe even slightly better than that, compared to your arm moving a mouse around to control a computer cursor. In terms of robotic limb control, people have shown compelling demonstrations of the robotic limb moving in a three-dimensional space and even some grasping movements. But the challenge remains to be able to use the neural activity to control, different fingers opening and closing, and sort of the multiple degrees of freedom that our arms and hands have. That's still a topic of ongoing research of how to control those well.
Yeah,
is it just going to require a lot more neurons, or what holds that back? More finer control or that ability?
Yeah, I think there are sort of two parts of this. So one is probably more neurons. The other is better understanding how intended movements are being expressed by the activity of the neurons that we record. Right. So in other words, we need better ways to read out or translate the brain's information or code, right, in the activity that it produces.
So how fast is the current response? You think something. How fast does the cursor react, for instance, or the robot arm move compared to normally doing it?
We can actually beat standard human level reaction times. So the typical latency between when a neuron in primary lobar cortex fires and when the arm moves is about 100 milliseconds, so a tenth of a second or so. And we can get that information to a cursor in tens of milliseconds. So we can actually beat standard reaction times with this, which is kind of an interesting fact. It sort of makes you wonder, why is the delay between neural activity and motor cortex and actual arm movement so long when in fact the signals are there much earlier? And this is something that researchers are still struggling to understand.
Well, you say beat it, but you beat it by 10 times. It sounds like that's a lot. That's more than just beat it by 20%.
Yeah, I'd say we can beat it by about 50%. Yeah.
Maybe part of the reason is that let me back up. When you watch people interact with the system, how long does it take them to get trained on it, and is it hard for them to do because the reaction's so fast? Maybe they tend to overcorrect and fly all over the place because their thoughts are so fast.
Yeah, that's a great question. Most of the time, we don't decode it as fast as we could. Most of the time, we try and match the sort of natural latencies, so there isn't any obvious discrepancies between how the cursor is moving and how you expect it to move. And that turns out actually to be really important. Some of the early instantiations of these devices, the lags were a little bit too long. And if you've ever used a computer mouse that had a little bit of a delay between when you moved your arm and when the cursor moved, that actually causes your control to crash really quickly. And so it's important to match those natural latencies. The other part of your question is how long does it take to learn how to use these devices? And I would say that you can get okay control right out of the box, sort of right after implantation and the first time you start to use it. Within a couple of minutes, you can get okay control. And then over the course of a month, there's a learning process that happens where you get proficient control. And that's really the sort of thing that Dr. Yu and I are interested in studying. How does the brain reorganize in order to go from okay control to really good control? And what are the limitations on that process? How can we speed that process up? And what is it in the brain that's changing when you're actually doing that learning process?
Do you have any subjects? I mean, I would guess this is a permanent condition, right? Or do you have any subjects that were like this for a period of time, but they regained functionality in a limb so they could revert back to that form of control? Or do you have patients where only certain limbs are like this and other limbs are under the quote-unquote normal wiring and normal control to compare?
Yeah, all of the clinical trials that are ongoing in the U.S. right now are on permanent conditions. So, and I believe all of them are on fully quadriplegic patients, or at least people who've lost bilateral control on both sides. It might not be complete, but it's bilateral control. I don't believe there's yet any clinical trials going on with a person who has one intact arm.
Yeah, because that may be very instructive. You know, something happens and I lose my left arm, let's say, but my right arm still works and I control it normally. I wonder what would happen if I had an implant that I used just my left arm, you know, because then my brain would work both ways.
Mm-hmm. Yeah, and people are really interested in understanding, for example, with stroke, a lot of times what happens is you'll lose control out of one arm. So people are interested in trying to understand, can you tap out a control signal from the intact side of your brain to control that contralateral arm, the arm on the other side of the body that you. People are interested in seeing if you can tap out control signals for the arm that you've lost control of from the same side of the brain that's still controlling the intact arm. And so to see if you can actually multiplex two-arm control out of the single side of the brain or not.
Yeah. Well, also in a person that's quadriplegic, I mean, can these people still move their head and they can still speak, and can they do all that and move their face muscles and everything?
Yeah. So most of these are sort of high-level spinal cord injury patients. So you still got face control, you still have voice control, all of that's still intact, but you've lost muscular control for the limbs and trunk in many cases.
So in effect, they still are moving certain parts of themselves the traditional way. You know, I want my cheek to grimace or I want to stick my tongue out, I do it. But my arm now, because I'm quadriplegic, I have to use this system and think, you know, to use the robot arm or to control the cursor. Have there been interviews with these people to ask them what the experience is like, and have you picked up any insights from that?
Yeah. So those interviews are really interesting. So one of the early patients that was in a clinical trial that was being run out of the University of Pittsburgh, she was interviewed about her experiencing is using the device. What do you think about when you want to make the robotic arm move to the left? And she says, I just think move left. And so it's really cool that the robotic arm is embodied in that way, that you just think move left and the arm moves left. But it's hard to get sort of real insight from that. You know, all right, well, what does that mean about how motor control is happening? We actually have very little ability to introspect on what's going on in our own movements. I can think, flex my bicep, and my bicep will flex. But in terms of all of the computations that actually have to occur for me to grab a cup of coffee, we don't think about those consciously. We don't think, well, the coffee cup is on my retina and my arm is located to the side of my body, and that means that the movement vector has to be up and to the left. We don't think about any of those computations. And so your ability to sort of consciously monitor your motor control is in some sense a little bit limited.
Is it, instead of a robot arm, do we have the technology yet to do a brain-computer interface and then implant electrodes in your arm, let's say that's disabled, so you can control your own arm with your thoughts instead of with the traditional nerve pathways?
Yeah, absolutely. So there are groups working on this, right, where you can stimulate existing muscles, right? So if someone has a paralyzed limb, they can use the neural activity recorded from the brain and then use a computer to translate that neural activity into desired movements or desired muscle contractions, and then stimulate the muscle of the intact limb to get the arm to move.
Okay. So you've chosen instead to go the robot arm way and the cursor way, et cetera, right?
Yeah, I would say that, reanimating a person's intact limb is absolutely the way to go. If your goal is just to sort of restore a person back to where they were, then that's the way to go. Right now, those approaches suffer from some sort of fundamental difficulties that researchers are working to overcome, but are hard to overcome. So, for example, when you stimulate a muscle, you tend to stimulate the fast twitch fibers and not the slow twitch fibers, which means that the muscle fatigues really quickly. And so the muscle response to a stimulation on minute 1 and the same stimulation on minute 3 are actually different because the muscle is physically getting weaker. And those are really hard things to overcome. Coding algorithm, and you don't want to run the muscle straight to fatigue because then it's going to take a long time to recover. And so those are really hard scientific questions to overcome. In the meantime, working on can we train subjects to control robotic arms, and how do subjects actually change their neural activity during that learning process? What can that teach us about learning in general? These are the kinds of things we're interested in. And then, all of that technology is obviously useful for somebody who's missing a limb entirely. So, amputation and that sort of thing.
So what are you learning about your work so far? What are you seeing after someone's had an implant for a while? They're getting better, they're getting finer control. Do you then remove part of the implants, or do you change the implant, or do you add more neurons, or what kinds of things are you tweaking to that are giving you insight?
Yeah. So one of the things that we've been very interested in is how the brain learns. So if you imagine like giving someone a tennis racket and allowing them to practice with the tennis racket, then they're going to get better at playing tennis. So similarly, if you give someone a brain-computer interface and then you allow them to practice with it, they're going to get better at using the brain-computer interface. And so one thing that we've been very interested in is observing what changes in the brain when a user goes from being a novice to becoming an expert. And this is work that we've been doing in collaboration with Professor Aaron Batista's lab at the University of Pittsburgh. And a lot of this work was led by Matthew Golub, who was a PhD student and postdoc in our groups. And one of the questions that we asked was, what makes learning some tasks easier than others? And so we used computer interface to try to address this question. And what we found was that the ease with which one can learn to perform a task depends on how the brain is wired up, meaning that if the task is quote-unquote compatible with the way in which your brain is wired up, that will make the task easier for you to learn than if the task were quote-unquote incompatible with how your brain is wired up. And so one implication of this is that because each person has sort of their own history of experiences, how one person might learn more readily might be different from how another person learns more readily, right? And so in thinking about, how we teach our kids math or how we teach people new sports or new languages, right? I think, this an important implication of this is that when we're teaching people things, we need to maybe give people a more personalized training regimen or learning environment in which we take into account what they would find easier or harder to learn.
Right. So what else have you seen? How does the brain change in response to this learning? Can you tell? What are you able to see experimentally is happening?
Yeah, so there's some really interesting things going on. So first off, there seem to be very different types of changes when you first experience something and you just quickly adjust to it versus when you're given a long time to practice with it. And so you get very different types of of neural reorganization for fast learning versus slow learning. For the fast learning side of things, what looks like happens is that your brain is producing these neural activity patterns to control your brain-computer interface, and then what we do is we change the way in which neurons drive the cursor, and that's how we create a learning pressure in this experiment. So we sort of rewire how these neurons are pushing the cursor around it, and we say, all right, try and regain control of the cursor. And what we see is that the brain continues to generate the same neural activity patterns that it was generating before. It just starts to generate them at different times. So it says, this neural activity pattern used to push the cursor to the left, and now it pushes the cursor up. And so what you do is you rapidly figure out to generate that pattern when you want the cursor to move up. And so we call this, sort of recycling of your neural activity patterns. You don't learn to produce new patterns. What you do is you recycle the old patterns and you reassociate them with new movements. And that happens really fast over the course of, say, an hour or so. And over the course of an hour, you learn to reassociate those existing neural activity patterns with the new movements to regain some control of the cursor. So that's the fast learning side of it. And then over a period of days and weeks of practice, you actually learn to generate fundamentally new neural activity patterns. And so these would be neural activity patterns you've never shown before, but that are really effective at driving the cursor to move faster and more accurately to the target. And so these seem like they're fundamentally different types of learning mechanisms, and we're super interested in, how each one of them works, what's actually going on, which are the brain areas that are driving fast learning, and which are the brain areas that are driving slow learning, and try and tease these things apart.
Very interesting. So what do you think is going to be the future for the brain-computer interface that you're working on? I know we don't know when, because the research takes however long it takes. But what do you think is going to happen over the next, 3 to 5 years, maybe 5 to 10 years? Where do you think the breakthroughs will be?
Yeah, I think so. Right now, this technology is not yet in clinical use. So it's a laboratory technology, and it's still being developed. I think over the course of the next decade, you're actually going to see clinical translation. You're going to see these devices be used as a therapy for particular types of patients, probably starting with end-stage ALS patients and then moving to less severe cases. And I think that technology right now is getting good enough to certainly give a patient control, really good control over a spelling device, certainly to give a patient good control over a computer cursor so that they can run a computer cursor and interact with a computer just as if they had their own mouse and their own keyboard and ability to control those. You're going to see these devices used to control wheelchairs and that sort of thing. On the longer time scale, it's going to take a little bit longer to get control over robotic arms with real grasp control. Whether that's going to happen in the next 10 years or so, I hope it will. I think we're on the right track. I don't know if it'll happen in the next decade. And then the other thing that people are really interested in is restoring sensory input to the brain. So when that robot arm touches something, you would like the brain to register that touch. And so there's an active area of research trying to work on that. That's going to be a tough nut to crack, but I think they're making good strides on it.
Yeah. So in parallel with what Steve just described, what we're hoping that will be a major area of focus in the coming years is to use brain-computer interfaces as a tool to study how the brain works. Right? This is a new area that a somewhat small number of people in the field are currently working on, and we're really trying to push the way here in sort of demonstrating that brain-computer interfaces have a second really important use that people don't really think about or talk about as of yet, but is extremely important. And we think that eventually it will be on par in terms of, or we hope it will be on par in terms of its importance, where the two things are, helping people, which is what Steve just described, and then also better understand how the brain works, which is what we're focused on.
Right. So take that as an example. You can take that slow learning process that I was talking about, which takes days to weeks, where you actually generate these fundamentally new neural activity patterns that are really appropriate for the task, allowing you to push the cursor fast and accurately. Why does it take days or weeks to develop those, and can we speed that up? What is there about the training paradigm? How can we design a training paradigm that'll make that process happen over a single day or over a few days and not a few weeks? And then can we translate those insights into non-invasive technologies? Can we understand how to better structure training environments so that learning in general is faster? And maybe not just motor learning, but classroom learning, language learning, those sorts of things. And that's I'd say, the real end goal of the kind of research that we do.
Well, very good. I can think of all kinds of amazing steps forward. I guess this right now, this is like a one-way communication. You think something and then you affect something in the outside world. And I think, like you said, in order for the brain to register that a robotic arm is touching something, you need a communication back to the brain to stimulate it in the right way to let it know that, the robot arm has touched something, for instance, or it's encountering resistance. Is that right?
That's right, yeah. So right now you can see it touch something, and so you still got that visual sensation that's coming, and that's natural, that's still intact. If you couple that with the tactile sensation and with the proprioceptive sensation of where the limb is in space and how it's oriented, if you couple all those together, I imagine you'd be able to speed that learning process up substantially.
Well, yeah, once you're able to stimulate the brain back in the right way and give it feedback, I don't know, one thing that came to my mind is, what if you connected, someone with a brain-computer interface to another person with a brain-computer interface and see if they could speak, brain to brain without speaking? That would be pretty amazing. But you'd have to have that two-way communication to do that,
Yeah, and people have done this in animals a little bit, sort of give output from one thought, input into another, and you can do that sort of thing. And it sounds very sci-fi, very next level. In one sense, it's like true brain-to-brain communication. In the other sense, essentially what's going on is you're decoding some kind of intent, often a motor intent, move a robotic arm that way, and the person is sensing that motor intent. They could see it, or in this case, it's actually a stimulation in the brain. And so in that sense, it's maybe less magical.
Right, gotcha. Well, very good. I mean, the work you guys are doing is super important. It's got a lot of amazing implications. And any last thoughts that you want to impart where you see things going in the very near future? Or is it just, we're heads down, we've got a lot of work to do, and it's going to be a while before we, this goes clinical?
Yeah, right back to work.
Well, so what's the best way for listeners to get in touch with you if they have questions or ideas or collaboration ideas?
So our press liaison, it's actually in the room right now, is Emily Durham. And the best way to get in touch with us is through her. And her contact information is on the Carnegie Mellon website. You can call her or email her, and she can make sure that those inquiries get to the right people.
Well, very good. All right. Well, Professors Chase and thank you so much for coming. I really appreciate your time, and it's been very fascinating. Thank you.
Thank you.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.